Hello everyone, my name is Jiahe. I will present our paper about developing functional models for video conferencing applications to better understand the relationship between the congestion control and users' quality of experience. The top video conferencing services grew by up to 300% when the pandemic started, and the growth has not stopped since we discovered that we like to work from home. So video conferencing is likely to remain an important part of internet traffic, and it's good to understand more about how it works. We can start looking at the overall topology of a video conference. Video conferencing applications, or VCAs, are able to operate in two modes. The first is peer-to-peer. The clients start by contacting a signaling server to negotiate the connection. And after the peer-to-peer connection is established, the signaling server is no longer involved, and the clients will send media traffic directly to each other. The second mode uses Selective Forwarding Unit, or SFU. This is used when more than two clients connect to the conference, and each client will send its video to the SFU. Then the SFU will forward the video to all the other clients. So the SFU is important for scalability of video conferencing. Now let's look at the high-level architecture. VCAs use RTP to send a continuous encoded video stream over the network. So RTP runs on top of UDP. So when combined with the high bandwidth of the video stream, the VCA needs to implement a congestion control algorithm. And there are no standards, so these algorithms are often proprietary. The congestion control's job is to compute a target bitrate and deliver this to the video rate control mechanism, like shown in this picture. When encoding the video rate control will match the output bitrate to the target one. And these two mechanisms are implemented on both the client and the SFU side. From the user's perspective, the quality of experience, or QoE, describes how we feel about using the video conference. Many things can impact it, like video or audio quality or latency. In this paper, we focus on the video quality, and our goal is to build a functional model which describes how the congestion control interacts with it. There has been a lot of recent interest in video conferencing. Prior work generally understands the performance of VCAs by observation under different network conditions, but explanation is not provided. So we aim to enhance the literature by providing a method to explain the observations from ours as well as prior work. Our methodology is in three parts. First, a measurement and observation, using controlled experiments to understand the behavior of the congestion control and video rate control. Second is to analyze the results and decide what the VCAs have in common and what is different. Lastly, we will construct the functional models out of components that the VCAs have in common. This slide gives an overview of the measurements. We picked Zoom, WebRTC, BlueJeans, and Jitsi. These VCAs cover open and closed source implementations with different algorithms. And we separate the measurements into the two modes we mentioned before. For peer-to-peer, we use Zoom and a simple WebRTC client. For SFU mode, we use Zoom, BlueJeans, and Jitsi. And Jitsi is based on WebRTC. We used an automated system to collect video statistics and packet traces while controlling the network condition. And here are some results in peer-to-peer mode to understand the congestion control. We consider different bandwidth limits, latencies, and loss rates. In each graph, the x-axis is time, and the y-axis is the sending rate. If we look at the results in the top left, when removing a 256 kilobits per second upload limit at the end of the blue region, we can see how WebRTC recovers the sending rate more quickly, and Zoom uses a staircase-like increase, suggesting that it uses a bandwidth probing mechanism. Here are the video quality metrics, and we use frame rate, resolution, and quantization parameter, or QP, which describes the quality of each frame, and a lower value indicates a better quality. The video metric value is on the y-axis and video bitrate is on the x-axis. We can see that Zoom and WebRTC have different strategies for adjusting this video metrics. WebRTC tries to keep the frame rate at 30 as much as possible, but Zoom reduces the frame rate a lot at lower bitrate. But Zoom stops the quantization parameter from going above a certain threshold. So on the graph, it doesn't go above 27 or so. And this prevents the quality of each frame from degrading too far, which likely has a large impact on the user's QoE. Along with more experiments and results in the paper, we can start putting together the functional model of the client side. So let's start with the encoder. The encoder creates a continuous real-time video using the parameters from the adjuster. So the VCAs use different encoders, like Zoom uses H.264 and WebRTC uses VP8. Now we include the congestion control. The congestion control generates a target bitrate for the encoder, and in return the encoder can give the utilization of the target bitrate to the adjuster, which can change the QP or frame rate to improve utilization. Lastly, the encoder provides the average QP and number of dropped frames to the quality monitor. The quality monitor and other device monitors will signal to increase or decrease the target frame rate and resolution for the video. This gives another feedback loop to control the video quality, and a more detailed model is provided in our paper. We also collected measurements for SFU mode, and there are two architectures for SFUs. The first is simulcast, where each client sends multiple videos at different resolutions, and the SFU picks the best one. The second is scalable video coding, or SVC, where the client sends one video made out of layers, and the SFU drops layers if the bandwidth is low. Here shows a set of experiments, equivalent to the ones we talked about earlier. When there is a very high latency of 1000 milliseconds, BlueJeans still doesn't adjust its sending rate, so it's entirely insensitive to changing latency. And with 20% packet loss, we can see that Zoom's sending rate is mostly unchanged, meaning it's very insensitive to packet loss. BlueJeans is starting to reduce sending rate, and Jitsi has reduced it significantly. For the video metrics, there is a noticeable difference to peer-to-peer mode. So even though Jitsi is based on WebRTC, it behaves differently, like how it lowers the FPS with limited bandwidth. And this shows how the SFU can use a different video rate control compared to the client. So again, we can have the functional model of the SFU to show what it does to forward videos to one client. The congestion control receives M times n-1 video streams, where n is the number of clients and m is the number of simulcast streams. And then the prioritizer block will order the videos based on the sending client's activity, like when it last spoke. The prioritized videos are then rate controlled by the SFU using the target bitrate from the congestion control. The SFU picks the resolution using either the simulcast or SVC technique, and then it chooses the frame rate. So here we want to show you an example of how to use the functional model to try and understand some unexpected behavior. So we have the video statistics over time with a low bandwidth but stable link. Zoom changes frame rate and resolution periodically, while WebRTC is more stable, and the QoP for both changes rapidly over time. So going back to our functional model, based on the network condition we have, the congestion control will deliver a stable target bitrate. So this is not a cause of the changing video metrics. And the QoP is defined by the encoder parameter adjuster. So this is kind of the reason why it changes more differently to the others. It changes rapidly to maximize utilization of the target bitrate. For the FPS and resolution, the large-scale changes are caused by the selection block, receiving alternating scale up and down signals from the feedback loop from the quality monitor. And the smaller scale FPS changes are likely from the parameter adjuster, again for the best utilization. So to conclude, video conferencing is a new norm and will remain an important part of internet traffic. But VCAs have very different methods of congestion control and video rate control. So developing a generalized model can help our understandings. In particular, we believe this will be an important step towards predicting QoE. As future work, we are looking at other impacts on QoE, like the type of video conference and interaction between the user and SFU. We hope the models will be useful as everyone continues to investigate the interesting world of video conferencing. Thank you for coming to this talk.